Well, Michael, I wonder if you could give us your impressions of what we just saw and mission success.
Well, it's hard to tell what we saw there. I'm not sure. I'm not sure if the gain was set correctly or what. We had some confirmation from the mock that they did have a thermal signature.
Yeah.
I should mention that the 9 instruments on the trailing spacecraft, the LCROSS spacecraft, were exercised on the way to the moon. In fact, we took images on the way and images of the Earth, so we're confident the instruments performed as expected. At the time of the impacts, the mothership, the Lunar Reconnaissance Orbiter, our sister ship, I should say, was about 50 kilometers overhead. They will have their first, and so they should have been seeing this with their suite of instruments. They do their first data downlink in about 2 hours or so. So we hope to have the data, and I expect we will be receiving both imaging data and spectroscopic data from the host of ground-based observatories probably within the next few hours. I think it is fair to say that within this $79 million cost cap, as I mentioned earlier, the experiment had been optimized to produce the largest possible impact plume. And so I remain confident that this is our best opportunity to date to measure the extent of water ice on the moon.
So what we're seeing here is a replay of that impact. Let's watch it for a little bit.
Yeah, even though there were 9 instruments on the trailing LCROSS spacecraft, which you see going in here, they basically break into 3 categories. There was something called a flash radiometer, which should have seen the flash, and by virtue of analyzing that signal, we can make some inferences about the depth of the regolith and it's the makeup of the dirt, as it were, that was thrown up by the Centaur impact.
Right, so brighter flash means, you know, it hit rock, and dimmer means it hit dirt, essentially.
Right, and actually you would want a dim flash here because that is suggestive that you hit sandy material and you want to throw up as much of that as possible, and that's easier to throw up than boulders. Then there's a suite of cameras, visible, near-infrared, mid-infrared, that provide information once we analyze the signal, once we analyze the data on the shape of the ejecta cloud, which contains both regolith and hopefully water vapor. It tells us about the dust grain properties in the ejecta cloud and provides spatial context for the spectrometers. And then finally there is the suite of spectrometers. And most of the information, much of the valuable information, will come out of the near-infrared spectrometer, which provides analysis of the chemical composition of the vapor in the regolith and any possible hydrated minerals.
Michael, we've just brought up the
thermal infrared.
Yeah. I wonder if you could comment a little bit on.
Well, the blue areas are the cooler regions, and so the green and the red are increasingly warm regions, and so you can imagine the sun beating down on the south rim of that crater. That's why it's showing up as red. This is all false colored, of course, and of course we're aiming for the blue region, which is the permanently shadowed region here. The reason you have this many instruments is we're trying to tease out, particularly with spectrometers, the way I like to phrase it to people is we break light into its color constituents, and then we look for little squiggles superimposed on big squiggles.
Yes.
And the little squiggles are hopefully the signatures of water and other hydrated minerals. The big squiggles are just the electronic noise in the cameras, and so even though the data will become available to us in the next few hours from the other orbiting and ground-based assets, I anticipate it will take a couple of days before we can calibrate out the big squiggles and get into the little squiggles. And we want to have some redundancy in the instrumentation. That's why we have multiple instruments looking at slightly different wavelengths. So the whole idea here is to collect as much data as you can and minimize any ambiguity in the interpretations as you try to analyze those small squiggles.
Well, and we have redundancy not only on LCROSS, but of course with all the ground assets from the Earth, the Hubble, and LRO, like you mentioned.
As we begin to collect the data and we analyze it, If we don't find water, is that a significant finding in itself?
It is, because of the reasons I stated earlier, excuse me, and that is because the experiment has been carefully designed to maximize the amount of material thrown up. That's by the mass of the impactor. It is the largest impactor we have utilized on the lunar surface, and by the impact angle. We went in at an impact angle of over 80 degrees, so it's basically straight on. And so if we do have a negative signal when we finish analyzing the data in the next few days, it means one of three things. First of all, there may be no water on the moon, although that would seem to contravene the announcement made a few weeks ago from the other spacecraft. So that leaves two possibilities. It means there may be water concentrations, but it's at less than the 0.5% sensitivity of LCROSS, which has ramifications, potential ramifications on the ability to extract that as a resource. And the third possibility is that the water in the frozen water in the permanently shadowed regions is not uniformly distributed, but rather is in patches, and like an old Texas wildcatter, we may have hit a dry hole rather than a wet hole.
Right.
So that's part of the reason we sent the Centaur impactor and the following LCROSS spacecraft on separate trajectories at the end, so they would impact two possible points. I can say that regardless of the results of this experiment, whether we have detected water or whether we have established an upper limit through a null result, the results will help advance our knowledge by constraining the current models or explanations pertaining to the moon. Like all scientific discovery, it rules out some explanations. It may advance the likelihood of others. That's just the normal process of scientific discovery and advancing our understanding of the universe.
So all indications are that the instruments were working, and no matter what we find, it's going to be important.
Indeed. I should mention, too, that part of the reason it's going to take us a few days to tease out the right answer here is because if you return to my original 4 science objectives for the mission, we're looking for more than just a yes-no answer. We are looking for quantitative answers. And so it's very likely that when you assemble data looking for, like I said, small signals from a family of 20 observatories, they're not all going to give you the same answer. And so we need to cross-calibrate the results from each of the observatories, too. And they help reinforce our understanding and give us greater faith that we have come up with the right answer.
I really can't think of any other event that's similar where we had all of these assets trained on such a small area of the sky, if you will.
Yeah, certainly the only comparable event was the Shoemaker-Levy 9 impact on Jupiter. We had some advance warning of that, but this is certainly the first time we've deployed this network for lunar purposes.
Yeah.
Yeah, so this is kind of an exciting time for NASA Ames. We've had a mission. It appears we had a successful impact. Data will be
particularly exciting 6 months, I think, here at Ames. We had the launch of Kepler. The commissioning is complete. It's begun its science investigation, searching for Earth-sized planets in the habitable zone around other stars. I've seen some of the early data. It looks very promising. I think Kepler will, at the end of its 3.5-year mission, will determine the frequency of Earth-sized planets in the local universe. We have the LCROSS mission here. We had another small secondary launch a few months ago of a mission called PharmaSat, which was a biological experiment on a Department of Defense mission. We have more of those coming up, and then, of course, next month we start open-door flights on the Sophia infrared. Pete Ward may have more to say on that shortly, but the primary purpose of that mission will be to study the thin, tenuous lunar exosphere before astronauts go back to the moon and start disturbing that exosphere.
I guess one way we could say it is that there is small satellites like this are not going to replace the big ones. We need the big ones, but there is a place for them. Would you agree with that?
I've always believed that. I think if you look at the various National Research Council Academy studies that come out every 10 years in the various space science disciplines, they consistently advocate